Welcome back to week 5 of our course, Boltzmann Law, Physics to Computing. This is the second lecture for this week. Now, in the last lecture, we outlined this transition from adiabatic quantum computing to gated quantum computing. That's last week, we were generally talking about quantum systems in equilibrium described by this density matrix, whereas we are now going to talk about isolated systems, and these systems can be described by a wave function. We don't quite need the density matrix. It can be factorized into these wave functions, and these wave functions evolve in time according to quantum gates. And the next 2 or 3 lectures will be about how we use quantum gates to do useful, interesting things, right? And they all have this structure where you apply one gate after another sequentially, and it's convenient to draw the time axis going to the left so that you start with a wave function at this end and you gradually multiply by u these different gates to obtain a final wave function. Now, one gate that's very interesting and important, that's widely used, is this Hadamard gate. And this lecture will be talking about the Hadamard gate. And it's this U matrix, that's this quantum transition matrix or this transformation matrix, the one that transforms the wave function from one point to another. It's given by this matrix for a single qubit. It's a 2 by 2 matrix. And you'll notice there's a -1 for this element. Okay. Now, if the initial state is, say, up, the initial wave function is all up, then if you multiply it with this matrix, and you can multiply it directly, and you'll see what you'd get is a superposition of up and down. Now, if the initial state is down, and you multiply it with this matrix, again you'll get a superposition, but now the down component will have a negative sign to it. Okay. Now, of course, if you ask for the probabilities, the negative sign doesn't matter, because the way you get probabilities is you take wave functions and square them. So you'll get half up, half probability of being down. Now the point is that this is a lot like what you might have got with a probabilistic circuit. The equivalent probabilistic thing, the classical thing, would be a W matrix that looks like this, where if you come in with the initial probability distribution function that looks like all up or all down, what this matrix will do is transform it into half up and half down. And here, it doesn't matter whether you started all up or down. After this, it becomes 50-50, and you get there. So you might say, well, then what's the difference? I mean, why are we talking about this special Hadamard gate? In effect, it's doing much the same thing. Well, that's only because we are looking at the effect after one gate. What's striking is what would happen when you apply the gate twice. So if you put the same gate again, then you see the effect is to multiply these two matrices. So it's the same U again. And the interesting thing about the Hadamard gate is that U square is actually the identity gate. So you can multiply it out and see. So what that means is when you apply it twice, you get back what you started with, because it's basically like an identity matrix multiplying that. So if you're all up, you end up being all up. If you're all down, you end up being all down. By contrast, of course, in the classical case, if you apply that same gate again, you will again get 50-50. So here it doesn't change, but here there is a big change. So now if you look at the probability distribution, classically you'd get 50 up, 50 down, half-half. Whereas with the Hadamard gate, if you had started all up, you'd be all up. If you started all down, you'd be all down. And this is the very interesting thing, that this negative term is able to accomplish. That is, when you apply the gate once, it spreads out like it's all over the spectrum, and then you apply it again and it comes back. See, that's the remarkable thing that you can do. Now let's consider what happens when you have 2 bits and you apply this Hadamard gate individually to each bit. Now with 2 bits, in general, it's better to think of it as a composite system which has 4 states, and these 2 individual Hadamard gates can be written by a single transformation matrix, which is like the Kronecker product of the 2 individual ones. So these were all 2 by 2 matrices. When you take a Kronecker product, you get a 4 by 4 matrix, and that's what transforms these composite states. So the composite states are now given by 0, 0, 0, 1, 1, 0, and 1, 1. So if you start out all in the 0, 0 state, then what would you get? Well, you see, you have to multiply this wave function by this matrix, which effectively is the same as looking at this column. You see, because the way you do matrix multiplication, as you know, you multiply rows into columns. And here, since there's a +1 here, after multiplying, you just get back this column out here. So if the input is 0, 0, that's the 0 state. The output is this, a superposition of all 4. Well, if the input is 0, 1, then you see you have a +1 there, and then you get again all 1s, but some have negative signs now. So it alternates, +1, -1, +1, and -1. Okay. What if you put 1, 0? That means you start with a +1 here. Well, now you get 2 +1s and 2 -1s. And if you start with 1, 1, that means you start with this +1 in the last one, then you end up with 1, -1, -1, 1. So in every case, you see it's spread out over all the 4 states once you apply this Hadamard gate, but with different combinations of signs. And if you looked at the probability distribution, of course, signs don't matter, so they would look like they were spread out 25% in each possibility, 0, 0, 0, 1, 1, 0, and 1, 1. But as we noted with 1 qubit, the thing is about the Hadamard gate is the magic of applying it twice. So when you apply it twice, if you multiply those 2 matrices, well, you then get the identity matrix that you can check. And what that means is after you apply it twice, you'll get back what you started from. So if you started with 0, 0, you'll get something peaked right there. Started with 0, 1, you'll be peaked in 0, 1. 1, 0, it'll be peaked in 1, 0, and 1, 1, it'll be peaked in 1, 1. So that's the amazing thing about this Hadamard gate is, again, apply it once, it spreads out, looks like all the information's lost, it's all spread out, apply it again, and it comes back right where you were. Now, it's convenient to express this property concisely because, as I said, this is something that's widely used in many of these quantum circuits. So if you label these columns as 0, 1, 2, 3, which is like the decimal equivalent of this binary representation, then you could name each column according to that binary representation. So you could say H0, H1, H2, H3. So what's H0? It's this 1, 1, 1, 1 multiplied by a half. What's H1? Well, it's 1 minus 1, 1 minus 1, again multiplied by a half, so on. So each of these columns, we give it a name. And we also define what you might call something like a delta function, which is delta 0 means you only have +1 in the 0, 0 position. Delta 1 means you only have +1 in the 1 position, delta 2 in the 2 position, and delta 3 in the 3 position. So these are the inputs we had been considering, and these are kind of what you get after application of the Hadamard gate. And the interesting thing is that when you apply the Hadamard gate to a wave function that looks like delta k, meaning a +1 in the kth position, you get the HK, which is whatever the column corresponding to that position is. And then you apply it again to HK and you get back delta K, because applying UH twice kind of brings it back where we were. So this kind of summarizes the property of these Hadamard gates that I was talking about, that we discussed in detail. And the thing is, it goes way beyond just 2 qubits. If you had, say, 3 qubits, well, it's the same basic principle still applies. Now, of course, since there's 3 of them, the overall matrix, this bold UH here, is now 8 by 8, and the way you get it is by taking the Kronecker product of the elementary Hadamard matrices. So you have 3 of them, and you do that, and now you have 8 columns, which you could label from 0 to 7, and there would be these H0, H1, H2, etc. And the deltas you could define the same way, but that same property holds. So it's a property that holds even when you have, like, say, 10 bits, so that it's a huge matrix. It's a 2 to the power 10 by 2 to the power 10 matrix, but the same basic thing holds. And what we'll talk about next then is how these Hadamard gates, actually in the next 2 lectures, we'll talk about these 2 classic quantum algorithms, both of which actually make use of Hadamard gates and other things. But the first thing you'll see is they use the Hadamard gate to take a 0 state and spread it out, and then later bring it back. Thank you.